So I would say the first of the division algorithms, the most basic one, comes from the model. Okay? So our first step at an algorithm is the idea of repeated subtraction. And if we look at, for example, let's do the 18 divided by 5, I just want to keep subtracting 5. So the algorithm here would be to take 18, subtract 5, that gives me 13. Okay, I can keep going. 13 minus 5, that gives me 8. Well, I can keep going. 8 minus 5 is 3. Stop. I can't do it anymore. And I find it happens 1, 2, 3 times. That's my quotient with a remainder of 3. Now, that's all well and good for smaller numbers, but when the numbers get bigger, it becomes a little bit more tedious. So for another example, suppose I had 337 divided by 12. So then I would have to take 337 and subtract 12 to get 325 and keep doing that over and over and over again. So that would give me 313 and this is going to go on for a while, but there's some kids that are tenacious and they'll just do that because they get it and they don't know another way. And I keep doing this until I get a remaining number that's less than 3. That's my division algorithm. So repeat until remainder is less than 3. Then I just count. So that's going to take a while. So I think we need to advance this algorithm a little bit. And so the way to do that is to do a grouped repeated subtraction, which involves multiplication. So we're going to come up to a better algorithm. And there's a few versions of this. So grouped repeated subtraction. And the groups could be big groups or small groups. So for example, for the 18 divided by 5, I know that 5 plus 5 is 10, right? That's the same thing as 2 times 5. So I could, from 18, take away a 10, because 10 is a nice number to subtract in most cases. 18 minus 10 is 5. And I just can make a note to myself that I just took out 2 5s there. And then 18 minus 10 is 8, isn't it? There we go. So I took out 2 5s there, and then I can do 8 minus 5. So that's 1 more 5 and get my 3 remainder. So I still get 2 5s plus 1 more 5 is 3 5s. So I still get the answer 3 remainder 3. Let's think about that with that other example of 337 divided by 12. So in this case, I would just want to look for bigger groups of 12. And you know, I'm pretty good at doubling stuff. Right? So I could say, well, you know, 2 times 12 is 24. I know that. And I can certainly take 24 from there, but I think I could do a lot more. For example, I'm really good at multiplying by 10, as are most people. So couldn't I take 120 out of that, 10 12s? So I'm just going to do that first here. So 337 minus 120 is going to give me, what, 7 minus 0 is 7, 3 minus 2 is 1, 3 minus 1 is 2, 217. Hey, I can do another 120, but I want to make a little note to myself that I took out 10 of them. And then from the 217, I'm going to take out another 120. So I'll make a little note, I'm taking out another 10. And 7 minus 0 is 7. 21 minus 12 is 9 on a good day. I can't do 10 of them, but, well, half of 120 is 60, so 5 times 12 is 60. I could certainly take out 5 of them. So what we do is look for easy multiples to pull out. Oops, no, it should be from 97, sorry about that. Make a note, I'm taking out 5 of them. And then that's 37. And I can't take out 5, but I could take out a bunch more. And it may be I or the kid doing this says, oh, I'll just take out 12 and 12 and 12, keep doing it if they can. Or they might remember, oh, I remember 3 times 12 is 36. And so I could take that 37 and remove 36, which is 3 12s. That leaves 1. So what do we get? 10, 25, 28. So it looks like the answer is 28, remainder 1. Okay. And so this technique is grouped repeated subtraction. I'm going to show another version of this in a minute. Sometimes the groups can be kind of random, whatever pops into one's head. Other times, pulling out 10 of something is pretty easy. If you can do 10 of something, half of that, 5 of them is usually pretty easy. And then there are other multiples people just happen to remember. I don't know about you, but I remember when I was a kid having to divide by 12 off to the side, I would go 12 and then 24, another 12 is 36, another 12 is 48. Anybody remember doing stuff like this on your paper when you were a kid? I totally remember doing that in elementary school. And I would just list as many as I needed to, 60, and just keep going to try and pull off a division like that. So let's try this again with a slightly different version of the grouping. And again, so far the algorithms I'm doing are just based on division means how many times can you subtract, right? Repeated subtraction. So let's call this 2b. And this is a grouped repeated subtraction with doubles. Doubles is something kids worked on starting in like first grade, right? Counting 2, 4, 6, 8. Learning how to double things is an important mathematical skill. And so the first thing we would do, given a problem, and let's stick with the 337 divided by 12, is we would make a list of doubles for 12. So 12 plus 12 is 24, right? So there's one group of 12, here's two groups of 12, and then I would say, okay, 24 plus 24 is 48. So that would be 4 groups of 12, and I keep going. 48 plus 48, 8 and 8 is 16, 96. That would be double 4, 8 groups of 12, and then we go again, 96, oops. 96 plus 96, 6 and 6 is 2, carry the 1, 18, 19, 192. That would be 16 groups, and I keep going until I surpass the number I have. So then 192 plus 192, I'm running out of room, is 4, 8, 384. Supposed to be a 4 down there. And that's 32 groups, but that's bigger than my number here. So it looks like I only need to look up to 16. And then I'm just gonna rewrite it a little bit different. I'm gonna kind of write it in the standard way we do for a lot of division problems. And this symbol is kind of different than a division symbol like that. And I'm gonna go back to something, I think it was Amanda mentioned. She used the phrase goes into. And the blue one up here is 337 divided by 12. And I can't really read this the same way because we usually read left to right. So if I start reading this from the 12, I can't say 12 divided by 337. That's totally not what I see here. That's 12 goes into 337. So it's a good idea to call this symbol something. It's not really a division symbol, but it is. It's different than this division symbol, but the numbers change direction. They changed orientation, and that messes a lot of kids up. So we have 3 division symbols, and we have the goes into symbol. Okay, so again, what do I mean by that? Well, we have this division symbol there. We also have the slash 337 slash 12, or we could write it as a fraction, 337 over 12. So the fraction bar is a division symbol, that forward slash is a division symbol, and this funky thing here is a division symbol. This right here is the goes into symbol. You could call it the long division symbol, but it is different than the other 3 symbols because it changes the orientation of the numbers, and that is troublesome for some kids. All right, so I write it in the goes into way, and then I just pick the biggest group I can in my doubles, which would be 192. So then I am going to subtract 192 here, and I'm going to make a note that I'm taking out 16 of them, and then do the subtraction. 7 minus 2 is 5. So I have to borrow there. So I got 145. And then I can't take any more 192s out, but I can go to the 96. I can take out 8 of them. So then I'm going to subtract 96, which is 8 of them, and then do the subtraction. So I got to borrow here. 15 minus 6 is 9. And then 13 minus 9 is 4. And let's see, so I'm done with 96, I go to 48. So subtract 48, make a note that you're taking out 4 of them. And subtraction there is pretty straightforward. We get a 1, and we're done. We didn't need any of the 24s. This worked out quite well. So what do we get? 16 plus 8 is 24, plus 4 is 28, with a remainder of 1, which I think we got it the other way using a different group repeated subtraction. So the group repeated subtraction with doubles is we make a list of doubles, and we make a note of how many doubles I have, right? So, or how many 12s I have in this case. So there's 1 12, 2 12s, 4 12s, 8 12s, 16 12s. I went to 32 12s just to make sure I didn't need any more. And then I start taking out the groups I need. All right, and there's some homework problems like this one right here, because this one is pretty orderly and systematic. My first version of the groups repeated subtraction was a little bit chaotic. I pulled out 10, I pulled out another 10, then I pulled out 5, but somebody else might look at this and be able to take out more or less. But the 10 times thing is a pretty good approach. Otherwise, we just work with doubles. And so that's grouped repeated subtraction. And then notice it's condensed here a bit more than the kind of we're subtracting singles over and over and over. All right, so we can do this a bit more, and it's most helpful if people know their multiplication facts. If they don't, it makes it a little bit harder. But doubling is not that hard. People can just do that just like I did here, right? Provided you know how to add, you can make doubles pretty easy. Provided you know how to subtract, you can then subtract those doubles and keep track of them. All right, next. So let's see, what are we on? Version 3 of algorithms. The next one is called a scaffolding algorithm. And it's more like the long division that you probably learned. So let's take again our 337 divided by 12. And we rewrite it with the goes into symbol. So then I say, all right, let's take 12 into 337. And you really want to practice that language and how to read this with the kids so that they get that order right. that they say divide when they see that slash with the dots, and they say goes into when they see this funky half box there. Then what we have to do is recognize that we know multiples of 12, that we know our facts, and that we know place value. So from 337, I could easily take a group of 10. I could take a group of 20. I can't take a group of 30 because that would be too big, right? 3 times 12 is 36. So 30 times 12 would be 360. So what I do is I just come here and say, okay, I can take 20 of these 12s out because 20 times 12 is 240. And we write all of these zeros in like that. And then we do our subtraction. So 7 minus 0 is 7. 3 minus 4 we'll have to borrow here. So that's going to be 97. And then again, we focus on the 12. And we're trying to see how many 12s can we take out. Well, let's see, 10 12s is too many. That's 120. 9 12s, 108, too many. 8 12s, 96, right? We got to know our multiplication facts. So then I can say, oh yeah, I can continue here. From that 97, I can take out 8 12s because 8 times 12 is 96. And then I subtract and I get my one remainder. And then the scaffolding is how I built that up here. And then I come down with filling in zeros. Some kids have troubles when you don't fill in zeros because they're not very neat. So we keep track of place values, we keep track of columns. And then from here I can say, okay, the answer must be 28 remainder 1. And to check that, we can always come back to our division algorithm. Right? That means 337 must be equal to 12 times 28 plus 1. And then we should carry this out either on paper or on a calculator. Right? So we would multiply out that right there. And we should eventually find some way that it's 336. Adding 1 to that gives me 337. And it matches what I have on the other side. So I get a check there. This is one version of the answer up there. So that's called the scaffolding algorithm. It's a little bit closer to the long division, but kids just don't start learning long division. Right? First we learn what it means to divide, then we practice it with small numbers that we know, and we work our way up to a system with bigger numbers. 2-digit, like 12, for which most kids have learned the multiplication facts related to 12. If kids don't know their multiplication facts, how can they possibly do this, right? The answer is if they know division is repeated subtraction, they've got some things they could do. And so you will see things like this taught in elementary schools these days to try and help the kids with a process they can do if they don't have a lot of facts memorized. Okay, next. What we refer to in this country as long division. And long division is like the scaffolding without the stacking of stuff vertically. And we kind of sort of ignore place value, but not completely. So let's again look at our 12 goes into 337. And often, since this is a 2-digit number, we look at the first 2 digits we see, the 33, and we ignore the place value in the 7, and we just ask, hey, does 12 go into 33? And we say, well, once, twice is 24, 3 times is 36. Oh no, it looks like it goes in twice because we know that 2 times 12 is 24, and then we can subtract. And so subtracting, what do we get? We get 6, 7, 8, 9, and then we bring down the next digit. And so we move across kind of one place at a time, and then we have to take 12 into 97. And again, if we don't know our facts, we get a problem. We might have to go off to the side and start writing down things like 12, 24, 36, 48, 60, 72, 84, 96, 108, 120, and then pick the closest one. Because 8 times 12 is 96, and there's our remainder 1. Okay, so this is what most of us learned, and we probably forgot that it was a progression that we had to build up to this. We didn't just walk into a class one day and they said, all right, this is division. Division started off with those simpler stories like, Gary has 12 cherries and wants to share it with 4 of his friends. How many does each friend get? And we draw these pictures to get the answers. So that's long division. We're going to take it a step farther and do what I've called short division. And I did demonstrate this in the beginning of this chapter. And this is taught in some countries. Oops. Short division. And with short division, what we do is this step where we do this, write the subtraction down, we kind of skip writing that step. We still have to do it, we just think it instead. So I'll do this a couple of times. So we're going to take 12 into 337. And like before, I look at the 12 and the first 2 digits. 12 goes into 33 how many times? Well, I think it goes in 2, because 2 times 12 is 24. And then I have to think, what is 33 minus 24? And hopefully I think correctly that it is, the remainder is 9. And I write it superscripted right before the next digit, because that tells me what I need to do next is look at the number 97. And then I say to myself, okay, how many times does 12 go into 97? 8 times, because 8 times 12 is 96. So I get it goes in 8 more times with a remainder of 1. So with the short division, we write a lot less, right? I wrote the 2, I wrote the 9, I wrote the 8, and I wrote the 1, but I skip writing the subtraction. We skip that part out. And that is short division. So we took this from one extreme where we had to subtract 12 singly, like one at a time, minus 12, minus 12, minus 12, count and do that 28 times. I've seen college students do this in algebra classes before, that they have a page full of subtractions on a test where they couldn't use a calculator because they didn't remember their multiplications. Nothing wrong with that, but the hope is that we get better at some of these algorithms. Getting better at some of these algorithms requires some memorization of facts. So if we don't know these 12 multiplication facts here, we really can't do long division. That's going to be out of reach for us, and we really can't do short division. So there are a lot of school districts that de-emphasize memorizing facts because they say, the kid's got a calculator. And yeah, we do have calculators, and we should definitely learn to use them wisely. However, some facts are necessary in order to solve more complex problems because a calculator only does what you tell it to do. So next we're going to look at some calculator stuff and some properties of division. Any questions on the algorithms? Again, so we have the short division, least writing. Long division is right up there with not writing much. Scaffolding, you write a little bit more because you fill in zeros for placeholders and keep track of place value. Double repeated subtraction, the grouped repeated subtraction that's kind of random, and subtracting one number at a time, which can take a while. All right, so I'm going to stop the recording here.